Good evening. Today we're gonna continue chapter 8 subjects. I'm gonna skim real quick through pulse accumulators and countdown counters. It should be easier to understand for you after all what we have done so far. Then we'll do PWM 16 and 8-bit modes with some demos. Last time we generated frequencies, digital waveforms using output compare. We explained input capture, output compare, and we did generate 1 kilohertz square waveform with a 30% duty cycle, and then we were able to change the pulse width through plugging in a number from the computer through the serial communication, and we have sent the signal on port T5, which is connected on our board to the buzzer. So we were able to change a sound. If you want to go further here, how to generate music and things, it is about delays and what to display. Maybe you guys know better me in music, because these are serenes for anthems and things like that. So we're done with this part. Let's go to real quick. And when we were talking about output compare, we said an action will happen on the output compare pin when the comparator discovers that both the TCNT timer and the output compare register are equal. So an event will happen on a pin, either a toggle or go up or go low. Sometimes in real-time applications, you will need or you are able to tie output compare 7, okay, to control other output compares, which means if output compare 7, the compare happens, you are able to make it also override the output compares from 0 to 6. Okay, yani 6, you programmed output compare 6 to trigger to go high or low when their output compare register is equal to the TCNT, but you're able to override it with output compare 7, which means if output compare 7 is met, you can make it trigger both 7 and other channels, okay, through these control registers. Also, there is another feature with output compare here in this controller. There is a forced output compare, which means there is a register, forced control register. Whenever you go right to 1 in any of these channels, so the output compare 7, the event will happen on its counter on its pin when the TCNT timer is equal to the output compare register. But at a certain point of time, whenever you want it to go trigger, go high, go low, whatever, you can just go right to 1 in the respective bit in this register, okay, to override. You don't need to wait for the counter to meet. This is really important in real-time applications. Here in the book, they're giving you the spark plug timing control. Sometimes you really need to trigger a spark without waiting for a timer or if something happens. In short, any of our controls, any of our output compares will trigger the pin according to what you programmed it whenever the comparator discovers a match between the output compare register and the counter, but you are able to go trigger that event whenever you want by writing to this register, this forced register. Examples. Okay, pulse accumulator. Pulse accumulator, I'm going to go through it real quick. The standard HCS12 timer, well, we have an enhanced timer on our controller. In this enhanced timer, we are able we have pulse accumulators. What is a pulse accumulator? It's like a register that whenever a trigger comes, a pulse, let's say, this counter or pulse accumulator will increment. It's a register that counts up. The pulse will act as if it was its clock. A rising edge came, the accumulator will increment. Okay, no need to write any code to detect if that pulse has arrived. The hardware will detect it, has a logic, and it will automatically increment the accumulator. We have 4 8-bit pulse accumulators, 4 registers that can count from 0 to 225. Pulse accumulator 0, 1, 2, and 3. We are also able to concatenate every 2 to create a 16-bit pulse accumulator. Yani pulse accumulator 2 and 3 can be concatenated to create pulse accumulator A, a 16-bit pulse accumulator that can count from 0 to F. Also, pulse accumulators 0 and 1 can be concatenated to create a 116-bit pulse accumulator called pulse accumulator B. These are configurations. We can use 2 16-bit pulse accumulators, 1 16 and 2 8s, 1 16 and 8 AC1, AC2, 116 B and A3 and A2, 8s, or 4 pulse accumulators, whatever your needs are. If you use 8-bit pulse accumulators, the pins that the pulse has to be connected to are port T0 to port T3 for pulse accumulator 0 up to 3. If we concatenate it and using 16-bit pulse accumulators, for the pulse accumulator A, the pin will be port T7, and for pulse accumulator B, the pin will be port T0. Here it is. So if you're using each one of these, port T0 there is a hardware that will detect the edge, and the pulse accumulator will increment automatically whenever a rising edge comes here. Okay, T0 for A0, T1 for pulse accumulator 1, and so on. If we concatenate 0 and 1, the 0 and 1, this will become pulse accumulator 0 and 1. This will become 0 and 1 are B. B will be 0. So port T0. If you concatenate 2 and 3, 2 and 3, this will be tied with port T7. Okay. Yeah. Here it is. Yes.
لا احنا حكينا انه هل الاكيوميليتر ممكن 8 بت ممكن 16 بت صح؟
Yes.
بنفس الوقت حكينا انه 1 بن هو مش زي الباراليل بورت انه بياخذ 8 بن.
Yeah, exactly. So you will detect a pin on this pin, Mustafa, a rising edge. So this accumulator, initially, مثلا you initialize it to zeros, it will go increment. First edge, it will become a 1. Okay. Then another edge came. Okay. This will increment again. It will become a 2. And so on. So it will be counting, accumulating your pulses, counting your pulses. تمام. And this can, on arrival of any pulse, this can generate an interrupt. Okay. We can configure the pulse accumulators in 2 modes. The event counting mode, which means whenever a pulse arrives, the accumulator will increment, period. The gated accumulation mode, whenever a level on the pin is active, yani high, the pulse accumulator will be clocked by the E clock divided by 64, running, counting. When the signal on port T7 goes low, well, inactive, let's say, inactive, the counting will stop. So you have a gate. Whenever you have PT7 enabled, the counter will be counting. When this is disabled, yani it goes inactive, it will stop counting. Okay, you can use it as a timer if you want with this counting speed. Okay, the pulse accumulator has two interrupt sources on port T7 for pulse accumulator A, and the pulse accumulator counter overflow. Okay, so an interrupt can be generated on a coming edge or on an overflow of the accumulator. Pulse accumulator B, this is for A. For B, for 3 and 1, the 8-bit pulse accumulator can generate interrupts. These two pulse accumulators can interrupt whenever their counters overflow, when they get to the 255 and overflow. For pulse accumulator B, the 16-bit, whenever its upper 8-bit counter overflows. Okay. Okay, these are the control registers. And at this level, I believe we can go and look at the pin, the bits in each register and be able to program it. So I'm gonna, because of tight time, I'm gonna move real quick. I have prepared a demo for you guys. I'll compile it and put it, but I can share where is the code. So it is, I have created this pulse accumulator, this code real quick if you want to look at it, to understand what's the point here. So here I have a 7-segment display, okay, and I have the interrupt 18 handler that will, this is an interrupt service routine that will, the program counter will come into here every time an edge arrives, okay? Pulses, the pulse accumulator, the 16 bit pulse accumulator. The register in Code Warrior called for pulse accumulator A is called PACN32, okay? First, I define port H as output to display the number, a number on it. Then initialize this register, the pulse accumulator register to 0. The control register, I configured it to 53. The control register is this one, 53. Where is it? 53 pulse accumulator. Where is it? The control register, pulse accumulator, control register 53, 1. So I enabled here 3 and 2, pulse accumulator A, 0 in the gated mode, in the counter mode. So 53. So I wrote a 1 0 1 0 0 1 1. Mashi. So here I enabled. Then I asked it to work in the counter mode. The edge is 1, and the mode is 0. So here we said PA pin low enabled. This is the no, we're working in the counter mode. In the counter mode, not this one. We're working here. So on a rising edge. You can make it work on a falling edge, but we did here on a rising edge. Then 0 0 for the timer prescaler. Okay, and this matters really, the timer, when we want to work in the gated mode. Okay, then 1 1 enable the pulse accumulator overflow interrupt, the overflow interrupt, and enable the pin interrupt. On every rising edge will get an interrupt, and this is the interrupt, the 18, number 18. Actually, so the code here is, so we wrote a 53, and here the loop, the infinite loop is empty, so I'm not doing anything. Okay, anything. I only configure the pulse accumulator to count on every rising edge. And here in the interrupt, every time I come in, I clear the flag and I display on the 7-segment display the value of the counter. I honestly already programmed it. I don't have, you can run, I'll share it with you. What will happen here? How to run it? You go to port T7, tie it to a button. For me, I tied it with the port M5 or whatever. Okay. Tie it to a button. Whenever you get a rising edge, the counter value will increment and you will see it on the 7-segment display. While there is nothing in your code that shows that you're incrementing anything. It's only detecting a rising edge on the pin and it will increment the value of the counter. Okay, so it's counting pulses. So I'll share this with you. Okay, let's move real quick. These are related registers. A lot of examples, pulse accumulators. Okay, there's TCT&T, the same principle, the TCT timer, that is the base of all input capture and output compare. One of you asked me, I think I forgot who, can we make this timer or count, it counts up from 0 to FFFF, 65,536. Can we make it count down? The answer was no, but we have another timer or counter that we can make count down, starting from high and count down to 0. Okay, and we can use it to generate periodic interrupts similar to TCT. I explained that how. Okay, we can trigger it to count down based on the E clock with a prescaler. We have the control registers. The Modulus Countdown Counter is called MCCTL register. Okay, it has a flag register. When it reaches the 0 and you triggered again, it will go back to 65,535, which is an underflow, we call it. For overflow for TCT, here it's an underflow, okay? And you can generate an interrupt based on that. You can control the timing, so you can make it underflow every amount of time you want. You can go get the reading of the timer at any time you want between any two events and use it to measure time. So a very handy timer as well. Okay. Some examples. Here, an example to make it overflow every amount of time, generate periodic interrupt, generate time delays using this way. Okay, now we know what are counters, how we can program their counting speed and use them as timers. Let's start with PWM. Any questions so far? All good? All good.
All good, Doctor.
Yeah, great. PWM, guys, we did last time we were able to generate a square waveform, a 1 kilohertz square waveform. Remember, 1 kilohertz with a 30% duty cycle, right? We used output compare to do it, right? And here was the math here when we computed what is the clock we're going to use, what is the prescaler, how many counts low, how many counts high. We did it, and we displayed it on port T5, and we were able to hear it. However, we were able to send this to a PWM pin and connect it to a motor, and when we were changing this pulse width, this will affect the motor speed, right? And I did explain what is PWM in the past, if you forgot. And we did an example actually using the Arduino with model based, if you remember. Do I need to remind you what was PWM? What is pulse width modulation? Everybody knows what is pulse width modulation is, the concept?
Yes.
Great, great. So in many controllers, to generate PWM signals to control motor speed, to control servo motor angles, to control light intensity, to control the amount of current flowing through any load in general, you can control how much time the current is flowing through a pulse width to enable a gate, open and close a gate, basically. Many controllers use the output compare peripheral or timer module to generate pulse width modulation signals, and that's what we did last time. However, if you remember, and if you look at the code we wrote last time, we were moving with the signal. We were in time. Did we reach this? Okay, next time you go high. Oh, okay, now we're high. Next time when the write the compare value register again and tell it to, when the match happens again, next time you go down, then give it a new value and tell it next time you go high, then give it a new value, the next time you go. So it implies a lot of overhead to program PWM signals with output compare. Now controllers have specific PWM modules that you can program. So we know what is PWM now, okay? In a PWM signal, when you generate a PWM signal, you need to specify two things. One thing is usually fixed all the time, which is the period. So when you want to generate a PWM signal to control a motor speed, usually the period is fixed, مثلا to 10 milliseconds, okay? And you will be changing this pulse width, okay, the duration of how much you're going to stay high between 0 to 10 milliseconds in this case. 0 will, which is stop, if this is a motor, if we're controlling a motor, and 10 milliseconds will be the maximum speed, right? Because you're always high here, or 0, you're always 0. Okay. Yes, I remember I explained the concept of PWM. Mashi, so usually the period is fixed, but you will be changing the value of the pulse width, the duty, we call it. Okay, so usually you have specific two registers, a period register, you write it once, and you have a duty register that you change according to your needs. So you'll be able to change the pulse width, make it more pulse width, less reduced pulse width, and so on. So how it would work, let me see so this is the principle. I'll talk about the clocks, okay? The pins, how it works. Here's how it works. I have a pulse width PWM period register and a PWM duty register, okay? And it is based on the TCNT timer, okay? Oh no, it is based on a timer subscaled from, it's based on a clock, okay? That is, we call clock A, clock B, and sub A, sub B. We'll talk about the clocks, but there is a clock counting here, okay? That we can control its speed, okay, an 8-bit counter, magic. The counter keeps counting whenever it's, so you write this value, you write it once, and you can write this at any point of time. Any of them, we can write it at any point of time. This counter will be counting at a certain speed. مثلا, a count every 1 second. You write a 10 here and 5 here. So 1, 2, 3, 4, 5. Now 5 matches 5. This will toggle the output. Okay, if you're high, you go low. If you go low, you will go high. Okay, toggle T. This is a T toggle register. T register. And it will continue. 6, 7, 8. After 5 counts, it will become 10. And this compare will show that this match. It will cause a reset. Everything will start over again. Okay, and the reset will also go reset the timer, the counter value. And keep doing this again. So your low toggle, okay, the duty is done, okay, you toggle, continue counting, the period is met, everything resets again, you go start from high, you count 5, toggle, okay, continue counting, you met the period, everything resets again, you go back from high, and so on. So you don't need to keep counting and changing the values and telling it what to do next time, okay? This is real quick. These are registers, the period and the duty registers, and the counter register. The counter, the duty, and the period. 3 registers, which are here in the counter, the duty, and the period register. These are all 8-bit, okay? We know in 8-bit, we can count from 0 to 255. This is the maximum. So if you're counting you're incrementing every 1 microsecond, so your maximum is 255, right? 255 microseconds. You cannot write more than 255 here. So the maximum period will be 255. Okay, you can make this faster. Make it count every 0.5 microseconds. So the maximum period is 255 times, or slower. Slow it down to 1 millisecond. 1 millisecond times 2, the maximum is 255 milliseconds. Okay, you have a limit. This is in the 8-bit mode of PWM. 8-bit mode. Okay. In this HCS12, we have 8 PWM channels, PWM 0 up to PWM 7, that are shared with port. I use the pin here, port P. Port P0, port P1, and so on. Port P. Every PWM channel has a counter that counts, and a period register and a duty register, 3 registers. Every one has its own counter, its own duty register, its own period register. And they all work together according to this block. Okay? The counter here is controlled through a clock source. Okay? A clock source. That is a sub of the bus clock, but we can scale it down further even. Now, we are able to concatenate every 2 PWM channels together so they can share their 8-bit counter registers and get a 16-bit counter, and share their 8-bit duty register and get 16-bit duty registers, and share their period registers and get 16-bit duty registers. Okay, in this case, they are also one of their pins will be the active one. In this case, when you configure them to 16-bit, you concatenate 2 channels. When you concatenate 2 channels, this will become 16-bit. This will become 16-bit. This will become 16-bit. Okay, 16-bit. Which means here now you will be able to count from 0 to 65,535. Instead, in the 8-bit mode, it was from 0 to 255, which is much more than this value, which gives you more options to create PWM signals, larger PWM signals. Okay, this is the basic concept. The clock sources that can trigger the counters here are prescaled clocks from the E-clock, which means we have 2 clock sources, a clock called clock A and clock B. Clock A and clock B. Okay, these clocks are subdivisions or are prescaled clocks from the E-clock, controlled by a PWM prescaler clock that are controlled using 3 bits each in this register, PWM PR clock. So if you go write 000 here, then your pulse accumulator, your clock A is exactly the same as the E clock. Okay. You can divide it by 2, by 4, by 8, up to 128. So the slowest clock speed for clock A is what? Well, it depends on the E clock. If our E clock was, E clock was 24 megahertz, يعني the time generated from the E clock is equals what? 1 over 24 megahertz was
0.04 microsecond.
1 divided 24 meg equals 0.04 microseconds. Thank you, Mustafa. 0.04 microseconds. The maximum we can go up to is يعني the longer delay, يعني longer time is times 128 is 5.33 microsecond. So max at 128 prescaler equals 128 times 0.04 equals والله نسيت الرقم was 5.33 microseconds. This is the maximum. Okay, per count. If you're using the 8-bit mode, using 8-bit PWM mode, then maximum period is what? Maximum period is 255 counts, صح? Times 5.3. يعني هاي times 255 equals how much? 1.3 milliseconds. 1.3 seconds. صح? 1.3 milliseconds. Okay? So using the E clock, prescaled 128, the maximum period that you can generate is what? Yani at 48 megahertz PLL clock, yani i.e. 24 megahertz E clock, maximum period using clock A with 128 prescaler is 1. I forgot we did the math here. 1.3 milliseconds. Oh. 1.3 milliseconds, which means that this is from a rising edge to a rising edge is 1.3 milliseconds. Okay. So, oh, sorry. If we store this, store, and divide 1 by this, this is 735 hertz. So this is your maximum frequency, 735 hertz. This is the max, which is not enough. So 1.3 milliseconds, yeah, I can barely drive a DC motor. So what if you want to control a servo motor that this period needed to be 20 milliseconds? We're way too far. Okay, we have a lot of options. How about if you want to do 10 milliseconds for a DC motor? We have several options. One can be slowing, well, we slowed down this timer with the prescaler to the maximum. Either slow down the PLL clock, that's an option, or take a sub clock. A sub clock, we can, instead of using clock A, we can use clock sub A. Sub A further divides this by 2 times a number that we write in a sub clock register here, sub clock A. Sub clock A, well, it's something that you can write with a maximum of sub clock A. It's right by dividing clock A by the value of PWM sub clock A register. I think it's 8-bit. Yani by 1024. Yeah, sub A is 8-bit. 8-bit, you can write 255 in it times 2, maximum meaning. So you can use clock sub A to further slow down and use a sub A instead of A as is, sub A. Or we can also concatenate 8 bits and make count instead to 255, count to 65,000. Anybody wanted to say anything?
دكتور بس انه انا بحكي هذا الفريكونسي وهذا السبيد للاوتبوت ويف فورم صح اخر شيء.
Yes, yes. للاوتبوت صح، لانه if you use the clock A as is, if you with 128 prescaler and you allowed it to count to the maximum 255, I multiplied by 255, didn't I?
Yes.
This is the maximum. The maximum is, this is the maximum value of the period register.
وهذا المينيمم فريكونسي اقل فريكونسي.
Yes, this is the minimum frequency and the maximum delay, the maximum period you can get. Okay. Higher frequencies will reduce this time. Did I answer you, Mustafa?
Yes, Doctor. Okay.
Okay. So we have several options. So we can choose clock A or sub A. Clock A is derived from clock E, pre-scaled with a number that we can control through these 3 bits, or clock B, that is also derived from the E clock through a pre-scaler configured through these 3 bits. This can be further slowed down to clock sub B, that is dividing a prescaler, dividing the clock B by 2 times the value we write in PWM clock sub clock B. Okay. The clock source selection. How do you say I want to use clock A or B, or sub A or sub B? This is controlled by the PWM clock register. And if you can see, you don't have full liberty to choose what clock source you want. Yani, for channel PWM channel 2, 3, 6, and 7, 2, 3, 6, and 7, you always have to use B or sub B. For 0, 1, 4, and 5, you always have to use clock A or sub A. And clock B is for some of the channels, okay? And clock A is for other channels, A or sub A. So, yani PWM 0, you have to choose clock A or sub A, period. Channel 1, also the same. Channel 2 and 3 have to use B, 4 and 5 have to use A, 6 and 7 have to use B. And there is a pattern here, by the way. Yeah. Anyways, and you're writing a 0 here or a 1, you will be selecting it for 0. 0, you're using A or a sub A. Okay. And here we're talking about the channel timers. We have the counter register for channel 0. So the X is 0 to 7. Okay, for all of them. A duty register, a period register. We have a polarity register to configure the polarity and enable. I'll talk about them. The polarity tells us what's the polarity going to be? Yani, is my PWM channel is going to be like this? Let me do it. Is my PWM channel going to be like this? This is the duty. And this is the period. Or is it going to be like this? Yani flipped. Yani the duty will be low and the rest of the period will be high. This is controlled by the polarity. So a 0 PWM channel is low at start of a period, then goes high for the rest of the time. A 1. The normal thing here, the polarity is 1. In this case, the polarity is 0. To enable a PWM channel, you write a 0 or 1 in an enable bit in this register, PWM enable register. This is how it works. PWM waveform alignment. We can make the PWM signal the left aligned or center aligned. Also, again, this is when we started the period, the duty high, then we went low. This is left. So here is the end of this is a cycle. Then we started another cycle here. We ended here. So our count high, the duty starts is aligned to the left. Okay. We can choose to make it in the center, something that would look like this. So this is left aligned. We started high, went low in the 1 polarity. In the 0, we start low and go high. In the center alignment, shows you how it works. In the center alignment, you start the duty, you go high for the beginning of the period, and in the next period, you continue at the same level and do the duty. It will be as if you were combining the 2 remaining periods, and now you got, this is the remaining of the period, but it's for the bigger signal, it looks like it's the duty, right? So this is center aligned. So the period, the duty, you start with it for the first cycle. In the next cycle, you end with it. You start with it, finish the cycle. In the next cycle, you end with the period. Okay. In this case, you are like concatenating the period minus the duty for 2 cycles together. Okay. In the 16-bit mode, we're concatenating every counter register, every polarity duty register, every period register is concatenated with another one. We can concatenate channel 0 and 1 together, channel 2 and 3 together, 4 and 5 together, 6 and 7 together, to get 16-bit numbers. In this case, the pins are the order is the same order as this. So the lower order is the 1. So if I concatenate channel 0 with channel 1, okay, the period register, the new period, the lower part is from channel 1, period 1, and the higher part, 8-bit, is from channel 0. Okay, 0, 1. Same for the duty. The lower 8-bit is from channel 1, the higher 8-bit is from channel 0. But for the pins, what pin are we going to use? We're going to use port P1 of the lower one. Okay, this describes it. Examples will make it easier. See, so the lower 8-bit of the duty and compare and period are the from the channel 1, and channel 0 will be the high. So 3 and 2, 5 and 6. But the pin will be of the lower one, and here it will be port P1. Okay, examples. I'm done, really, almost. Let me go do some 2 examples. DC motors, we know what DC motors we did. I'm going to come back. I'm going to come back to DC motors. And we use DC motors. I'll talk about edge bridges real quick, feedback. I'll use a servo motor today. Mashi. So let's go do some demos real quick. How much time do we have left? Okay, good. We have some time. طيب. What do I want to do here? Okay. Discard. So I have pre-prepared some examples. So let me do an 8-bit example, copy, go run an 8-bit example and a 16-bit example. The 8-bit, I'll show that the square waveform on the 7 segment on the scope. For the 16-bit, I'll use a servo motor. Okay. 16 class demo 16. Okay, this is some code I wrote in the past. I did some modifications on it today. In this demo, I'm going to be reading the analog to digital converter from channel 7, which is the potentiometer. In the 8-bit mode, the potentiometer will give me a number from 0 to 255. Tamam? From 0 to 255. I'm gonna, so most, turning the potentiometer to the maximum left will stop the a motor or generate a 0 PWM signal with pulse width 0, and the maximum right will be all 1, the maximum speed if I pass it to a motor. Okay, and I'm going to call my function motor 0 initiate or motor 0 speed. You can call it PWM 0 init, motor PWM 0 speed, but I'm going to use it for a motor, for most likely, whatever you can call it as what you want. I'm going to change the pulse width that I'll be passing to this PWM to change the pulse width. I'm going to read it from the potentiometer and pass it. I'll come back to these numbers later, after we understand how we did the math. I'm using a PLL init. I'm raising the frequency of the core clock to 48 megahertz, which is an E clock of 24 megahertz. And we did this in the past. So initially, PWM 0 always uses clock A. We saw that. Okay. For me, I'm not using A, I'm using sub A, clock sub A, because that's how I wrote PWM clock sub A. Polarity start high and go low. Prescale the E clock to the maximum 128. Mashi. Then prescale A with sub A of 8, which 8 comes from 4 times 2. 4 is what you write in the PWM sub clock A times 2. 4 times 2. I wrote 4 here, so 4 times 2, 8. This is what? This is, I wrote the math here. Then PWM control, disable, okay, select 8-bit mode, disable PWM in wait and freeze mode. This is how I did the math, guys. So if I go, I selected that my E clock is 24 megahertz. So 1 divided by 24 million, right? This is my initial E clock. I times 128 prescaler, 128. Then times 8, 2 times 4, the sub A, because I'm using sub A, times 8. So we will get 42 microseconds per increment. 42 microseconds for every increment. My goal here, guys, is to generate a PWM signal here of period 10 milliseconds. And be able to change this value. So 10 milliseconds in 8-bit mode. See? In the 8-bit mode. So the maximum number I can write to the period register can be a number from 0 to 255. We cannot write anything more than that. So what I did here, I have a count. Where's my calculator? Here. Every count will take 42.6 microseconds. Let me save it. Save it. And I want 10 milliseconds. How many counts do I need? 10 milliseconds is 0.010 seconds divided by the number I just saved that takes for each count, 42 microseconds. Then I need 234 or 235, 235 counts. Then with this free, I need for 10 milliseconds, 235 counts. Where did this number come from? 42 microseconds times 235 equals 10 milliseconds. Where did this come from? The 42 microseconds, it came from 24 megahertz, 1 over 24 megahertz, e-clock's time of the e-clock, pre-scaled by 128, and then pre-scaled again by 4 times 2, yani 8. The result of this is 42 microseconds per count. With 235 counts, I get the 10 milliseconds. It is 234 seconds. Point something. So let's choose 235. 235 times the 42 microseconds, I'm gonna get exactly 10.02 milliseconds. Yani I'm not gonna be able to get the 10 milliseconds exactly. 10.02 milliseconds. Well, let me write it down عشان we don't forget it. So we're gonna get 10.02 milliseconds. Yani 2 microseconds error. No problem. Got it, guys? So I did the math here in terms of frequency, then I did it again in terms of time. ماشي? So the maximum counter of the period is 235. This is how I got it, the 235. ماشي? 235. To get the 10.0. I commented on this. طيب, I want to start 50% duty cycle, so 235 divided by 2. تمام? Initialize PWM counter to 0, then enable it. Then it will start working. In the motor speed, I'm gonna just read the speed from this function, store it in the PWM duty. The duty initially is gonna be half speed, half the duty, 50% duty cycle. Then I'm gonna be reading it. I'm gonna read it and pass it to this function from the potentiometer. So I'll be reading the potentiometer here, but the potentiometer gives me a value from 0 to 255. And I bet the maximum 235. So I multiply by 235 and divide by 255. So I get a speed here from 0 to 235. Okay? And I pass it to this function, motor 0 speed. This function will take it as is and store it in the duty. Of course, you can copy all this, create motor 1 function, motor 2 function, up to motor 7 function. You can control this. تفضل مصطفى.
يزيد دكتور ليش ضربت ب 235 وقسمت على 255 عشان نحصل عليه؟
Because Yazid here, A to D converter, you remember when we took it, in the 8-bit mode, the analog voltage from 0 to 5 volt is converted to an 8-bit number. The 8-bit number is maximum how much? Tell me انت.
255.
Yes, 255. بس أنا my motor speed here at 10 milliseconds عندي are 235 counts.
235 عشان هيك بضرب بقصى 235.
So I want to scale it down. 255 أحولها ل 235.
شكرا دكتور شكرا.
العفو. So I time 235 divided by 255. Yeah, this is the closest I can do. طيب, let's program this. If you have questions, ask me please.
دكتور هون الديوتي سايكل انت حكيت 50% صح؟
Yes. Well, I'm going to change it with the potentiometer, but initially, this is the initial value. Yes. Did I program or not yet? The accumulation, serial monitor, program, COM3. Okay, programmed. طيب. Now, guys, let me go to my stuff. Let me turn on this camera. Let me stop sharing so you can see this better and highlight pin spotlight for everybody here. Now you see my phone camera, right? طيب. Okay. What do we have here? ماشي. So here's my oscilloscope. I'm gonna put the scope on port P0. ماشي. On port P0, and this is my screwdriver, and this is my potentiometer. Did I run yet or not? I didn't run. Okay, now it's running. I'm going to be turning this. I'm going to be turning this screwdriver, and I'm taking a signal here from port P0 to the scope. Okay, this is my probe to the scope, and here is my scope. And now I'm going to the maximum left. So we're at 0. So if this is connected to an LED, it will be off. It's connected to a motor through an NMOS transistor, similar to what we did in the motor example when we used the model based with Arduino. It will stop. I'm going to start turning right, turn right, start getting a PWM signal. See the pulse width? It's increasing as I turn right, keeps increasing. Now here I'm in the middle. The PWM signal I have, see the period is 10.1, 10 millisecond, 10, jumpy يعني شوية noise. And the pulse width, the square here is 5 milliseconds. So here I'm at 50% duty cycle. I'm incrementing. See here I'm almost at 75% speed or duty cycle. And here is the maximum. Now I'm high all the time. Okay, so here is your full speed. Okay, so I can connect this to a motor. We did this in the past. You can go, this pulse width. You can take it, connect it to your motor through an NMOS transistor by sending this port P0 to the gate of the transistor. And the motor will start turning on and off real quick, and you will be controlling its speed. We did the exact same example with the Arduino, if you remember. But now see, we're generating PWM signal as easy as that. This is an 8-bit example. Now I'm going to do a 20-bit example, sorry, 16-bit example. Let me go back here. Now I'll do a 16-bit example, and we'll see it on the servo motor. The servo motor, guys, I have ماشي, so I'll share this demo with you. For the servo motor, يا شباب, I have shared with you some data sheets on the e-learning. for several servo motors. This is one of them. For example, a small size servo motor, something like this one I have in my hand. This is a very small one. And see my hand size, a small one. It has 3 lines. You see my camera, 3 lines. Usually red is the VCC, the power, brown is ground, orange is PWM. Sometimes this is black and this is yellow, no problem, same concept. Most 99.99% of servo motors period are صارت as a de facto 20 milliseconds, 50 hertz. ماشي? So 20 milliseconds. If we do the math using the same clock we used in the 8-bit mode, I just showed you in this example on the scope. You need 235 counts, which is close to 255. Yani. We got the 10 millisecond. How do I generate 20 millisecond? We need either to slow down our clock or count more. Now we're going to count more. I want to count a number more than 255 in thousands. So I'm going to concatenate 2 channels, okay, to get the 20 millisecond. How do servo motors work? You control usually the duty cycle, the pulse width, from a number from here. For this one specifically, it's from 1 to 2 milliseconds high, and the period is always fixed at 220. 1 corresponds to the maximum left. Yani a servo motor, you know a servo motor, صح? So this is a servo motor. This is a normal size servo motor. A maximum left. So, well, servo motors, some of them are, well, it is hard to move. Yani. Let me just reset. Servo motors, really, and I cannot turn it in my hand. It's really hard. Servo motors, sorry. Come on. طيب. Some of the motors are 45 degrees. You turn this angle. You turn an angle. It has multiple heads, head shapes. You can have an X size, something leaner like this to turn, to go up, down, or whatever, to open something, close something. This one on the screen moves from 1 to 2 milliseconds, needs 1 to 2 milliseconds to control a degree from 0 degrees position at 1.5 millisecond, middle 90 degrees, 2 milliseconds. Okay. Minus 90 is all the way to the left, 1 millisecond. Some of them go even lower. Yani the one I have in my hand is something from 0.9, 0.8 millisecond up to 1.2. Some of them go 1.3 millisecond pulse width. So you can Google and find a lot of data sheets for servo motors with different values, but the period is 10 milliseconds. Here's the other one. Here's the other one. Yani standard size. If you come to the lab, we have this big size, okay, really big ones. This is a normal size, okay, and we're talking about the angle we're controlling here, how far left or right we can turn this thing. ماشي. Same connection, power, ground, and PWM signal. The PWM period is 20. Here, the duty cycle is should be something somewhere here. Oh, this is a speed or what? Some of them are angular servo motors. Yani the servo motors I had here, I thought, and I asked Mahmoud Wallah to give me one that rotates 360. Okay, now these can rotate, some of them 45 degrees, 180 degrees, and you are able to change the pulse width to change the angle they're at. Some of the servo motors are 360. And the pulse width in that case will control the speed of how fast they're turning, okay? Usually the middle is 0, going more and the middle, let's say, is 1.5 milliseconds. Start increasing over 1.5 milliseconds, you start rotating clockwise, faster, faster, faster. If you go below 1.5 down to maybe 0.7 milliseconds, you start going in counterclockwise in the other direction. The further you go from the middle, you go faster. Okay, those are the 360. Anyways, the concept is we need to generate 20 millisecond. I also wrote the code for that. Generate 20 millisecond. Let me go with it over it with you and run it on the servo. Copy. Let me start a new program. I think our plan will work for the operating system next time. طيب, class demo 17. I skipped the pulse accumulator one. Maybe I'll need to renumber. But the notes I put in e-learning are clear usually. Okay. Here the math is a little different. I use different values for the clock. Let's just to make sure no problems. Okay, yeah. So here, guys, the same thing. And I want to initialize the PWM, but in the 16-bit mode to be able to count more than 255. And then change the value of the pulse width to change the angle of the servo motor. So I call my function servo 0 initialize and servo 0 angle. You can call it PWM 001 init, PWM 01 angle or pulse width, whatever. You can call it whatever you want. Here I'm going to read the pulse width from the analog to digital converter from the potentiometer, pass it, convert it to an angle, and pass it to the servo angle. So I turn, the servo will start moving according to my potentiometer. طيب, initially PLL init, okay, A to D. Okay, initialize the servo clock. I'm using clock 0 and 1, channel 0 and 1, concatenated. Okay, so clock A, prescaler of 16. So clock A, prescaler of 16, we get 0.66 microseconds per increment. That's it. I'm not going to use sub A. Then concatenate PWM 0 with 1. Okay. Polarity start high. And this is it. So let me show you the math. The math is, I'm using 16, yes. I'm using the 1 divided by 24 million, 24 megahertz clock times 16 prescaler. So this is the 0.6666 microseconds. So let me store it. 0.66 microseconds. طيب. Now I want 20 milliseconds. How many counts do I need? 20 milliseconds is 0.02 divided by what I just stored per count. So I need 30,000 counts. 30,000 counts. After 30,000 counts, I'll get the 20 milliseconds. Got it? Per increment. So the period 20 milliseconds is 30,000 times 0.66 microseconds. ماشي؟ طيب, this 30,000, I need to write it in 2 registers. 30,000 cannot fit in one 8-bit register, صح guys? One single register 8-bit is 255 maximum. طيب 30,000, it can fit in 16-bit register. 16-bit register, 16-bit register, 16-bit. In this case, this is the period low, and this is period high, صح? This comes from PWM channel. Come on. بطل يكتب هذا. Okay. Okay. Battery problem. Okay. What happened? بطل يكتب قلمي يا اخوان. I'm sorry.
لو الجزء انا محطوط على التكست مش على مش مختار الماركر.
Really? Okay, thank you. طيب, شكرا يا احمد. Okay. طيب, so here 16-bit. This is the PWM channel 1, and this is from the PWM channel 0. We have two complete registers. 16-bit can hold a number up to 65,536. صح? طيب, and I want to write here 30,000. 30,000 is a 16-bit number, صح? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I want to take the lower 8-bit, write it here, the higher 8-bit, write it here. So what do? I take the 30,000, shift it right 8 times. This is the symbol for shift in C, and store it in period high. Then I want the 30,000 and it with 0x00ff, يعني cast the higher 8-bit and keep the lower 8-bit and store it in period low. Got it? Okay. So this is what I did. I took the number 30,000 that I computed here, shift right 8 times, store it in the lower register. And 0 هي high, لأنه 0 is high, in 1 is low, and it with FF. Same for the duty. I'm going to start the duty at value 2000. 2000 is what? Is this value اللي هي يعني 1 divided by 24 megahertz اللي هي I keep forgetting numbers. Yeah, times 16 prescaler اللي هو 0.66 microsecond. Let me store it. Okay, then times 2000 ولا ايش هي كانت 2000 ولا 20,000 2000 1 2 3 1.3 millisecond. So I'm going to start with 1.3 millisecond. 1.3 millisecond is something close to the maximum, right? ماشي. 2000 is also يعني more than 8 bits, so I need to store higher 8-bit in the higher byte, lower 8-bit in the lower byte, enable the PWM channel. And during the running, I'm going to be changing the angle, which is the value of the duty registers here that I wrote the 2000 in. Something called my angle. I'm going to read it from the servo motor. طيب. The servo motor is going to give me a number from 0 to 2 to 55. Sorry, from the potentiometer, sorry. Channel 7 is going to give me a reading from 0 to 255, صح? 0 to 255. This number, I want to scale it. I added 1,000 to it times 7. يعني ايش؟ يعني minimum is going to be 1,000. 1,000 اللي هي count يعني 1,000 times 0.66 microsecond is going to be 0.66 millisecond. The maximum low. ماشي. And the maximum is when the reading is 255 times 7. 1,785 plus 1,000. This is 1.85 milliseconds maximum. So I'm going to be moving when. So my pulse width modulation is going to be between 0.6 milliseconds to 1.85 milliseconds. ماشي. Here I'm going to be changing the value. This is what I'm generating here. I will see it on the scope and as well. I don't know. It's not writing, and I'm choosing the. شايف يا أحمد؟ أو معلق والله ما أعرف. Okay. I'm doing 20 milliseconds period. I'm going to be changing this from 0.6 milliseconds to 1.85 milliseconds. Okay. This is what we're doing here. Let's program it, run it. لا ما simulation. I'm almost done. whoever has to leave can leave. بس يعني this is I'm gonna finish the demo on. Well, بضل ال H bridge, I'm not sure. Let's see. Okay. Programming. Okay. Running here. Let me close this. Let me stop sharing. Close this. Live spotlight the other camera. Where's the other camera here? Remove. Okay, you see my other camera. What am I going to do? Okay, did I run it? I'll run it. طيب. Now, first thing, we concatenated two channels. So I moved to port P1. Port P1. This is what you see on the 7-segment display, on the scope. I'm going to be turning the potentiometer here from maximum left to maximum right. And this is what you see. So this is maximum left. See, the period is 20 milliseconds. Yani 5 milliseconds per square here. See my, okay. 5 milliseconds here. 5, 10, 15, 20. So the period is 20. And let me yani zoom in to see the pulse width. So the pulse width will be from maximum left. So 1 millisecond per square. So this is almost 0.6 millisecond, 0.66. Keep incrementing to 1.8. Okay, this is the maximum. Back to here, same thing. Now, if you want to see this on the servo motor, just I'm going to connect my servo motor connected here. ماشي. Connected red to battery high, brown to battery low, and the orange to port P1, which is the PWM signal. But make sure not to forget the common ground from the battery to the microcontroller, because the PWM needs to have the same reference. Let me get my battery here. Let me just okay, connect the battery. And here I want you to look at the servo motor. I'm going to be turning from maximum left, maximum left, right. I'm moving right. I can stop it. When I stop moving, you can see my hand and the 7-segment display and the motor. I'm sorry. Maximum right, maximum left, maximum right, maximum left. ماشي. ماشي. Clear, guys? Pulse width, I change the pulse width, right to left, change the pulse width, you got maximum left, maximum right, and so on. Clear?
Clear.
Clear, yes.
I'm done with this demo. So now we know how to do 16-bit PWM signals, PWMs, and 8-bit PWMs. I'll share this with you as well. طيب, for those who have to leave, can leave. And here is almost everybody knows what an H bridge is. DC motor control. Now we know how to control DC motor. When you control a DC motor, you can read feedback through a sensor, how many rotation per minute, RPMs, right? And be able to use a control loop to increment and decrement. Last time we used the driver. The driver was an NMOS, and I used it to go back to the demo where we controlled the motor with model based. Okay. There is something called an H bridge. Do you know what an H bridge is? I can leave it for next time if you want. Anybody doesn't know what an H bridge is? عادي يسألوني. I didn't know when I was when I finished my undergrad.
أنا ما بعرف.
Okay, so طيب, okay. Let's do this the first time next time. The first thing in the on Wednesday, I'll explain what is an H bridge. and how to use it to change the direction of the motor. Okay, it is used to control the direction of a motor. It's in addition to the speed of a motor. Okay, so I'll.
دكتور مش كان برضه ممكن انا اعمل زي كونفرتنج للفولتج او ستيب اب ستيب داون، انه الموتور بيشتغل 12 فولت وانا عندي 5 فولت، ممكن اعمل هيك عن طريق الاتش بريدج.
Wallahi, I'm not sure if I understand your question. An H bridge, Mustafa, is to control the flow of how the current is flowing from right to left or left to right. So you can make the motor turn in a way, instead of going to reversing the polarity of the battery, you can control it electronically. Okay.
تمام.
يعني stepping up the voltage, I'm not aware. And the normal H bridge doesn't do that. No. طيب, I'll explain H bridges next time. And we'll start, inshallah, with real-time operating systems. Thank you very much. I'll stop here. If you have any questions, you can stay until I stop the recording. See you Wednesday.